This is Lab 3 Black Hole Orbit. The objectives of this lab were to analyze the motion of a star orbiting a black hole by modeling the components of the force acting upon it, given the mass and position of the Sun relative to the black hole. Then, the mass of the black hole would be determined using the magnitude of the force calculated. Some important equations are that the net force is equal to delta P over delta T, or dP over dt. Also, dP over dt is equal to the parallel component of change in momentum plus the perpendicular component of change in momentum. And the magnitude of net force for gravitational net force is equal to G times m1 times m2 over r squared. From this equation, the mass of the black hole can be calculated, which equals the magnitude of net force times r squared over G times m1. The line of code that calculates the mass of the black hole is shown here. In the code, I changed the mass of the star and delta t. I also changed the velocity in the x direction to be delta x over delta t, and in the y direction to be delta y over delta t. Then, using the velocity, I calculated the initial and final momentum, which I then used to calculate dp dt as delta p over delta t. Then, to calculate the parallel and perpendicular components, first the parallel was magnitude of p final minus the magnitude of p initial over delta t, and the perpendicular component, I just did dp dt minus the parallel component. Finally, I printed the time and the mass of the black hole for each iteration. When the program is run, it shows the arrows representing the different components of momentum in a circular orbit, and down here it prints the time and the mass of the black hole during each interval. This is a graph representing the mass of the black hole at each interval. There is a large variety of different masses, so I put the max and the min, as well as the average black hole mass, which was 1.58 times 10 to the 35th kilograms. When considering how Fnet relates to the change in momentum, I looked at the equation Fnet equals dP over dt, and also Fnet equals Fnet parallel plus Fnet perpendicular, which means the parallel components of Fnet and to the change in momentum, as well as the perpendicular components, are equal in magnitude and direction. The difference is Fnet is found by adding the forces acting on the system, while change in momentum is found by analyzing motion. The net force can be used to calculate a new momentum, and this change in momentum can be used to vice versa calculate the net force. If a different black hole was in position of the one in the experiment, it would not be possible to find a different mass, because Fnet was calculated from the change in momentum over change in time, which was found from the change in velocity, which was calculated by the change in position over change in time. So an Fnet depends on position. However, since the motion of the star did not change, the position would remain the same, as well as the mass of the Sun. So according to the equation, m2 would have the same value, and it would not be able to have a different mass for the black hole. In conclusion, the gravitational motion of an object depends on both its parallel and perpendicular components. The components of a net force are equal in magnitude and direction as the components of dp dt, which is proved by the momentum principle. Finally, the calculation for the mass of a black hole in this experiment depended on its position, so if motion remains unchanged, it is not possible to calculate a different mass for the black hole.